What I really want to do is sort of conclude things here. And I want to conclude things with a sort of a philosophical discussion, maybe, about how we can change programming. Now, I think programming is great fun and also very useful when it comes out with good stuff. But for the most part, I see that we're doing it wrong. Okay? If I look at the history of people writing programs, what you find is that it's very, very detailed work, often rather painful. That's fine. There's nothing to be gained very much without work. But the problem is that a lot of the work is done over and over again. And the reason it's done over and over again is because each piece that people make is somehow flawed in a way that it can't be used for other things. Okay? That's one thing that's a very clear observation. Another thing that you see is that we, just from a cultural point of view, we have very large numbers of programmers, most of whom don't get anything done at all, and a few people who do almost all the work. And that's probably due to the fact that we have to think that redundancy somehow is the right thing. I'm not sure. But in any case, if I look at a slightly different business, there are people who've been designing things for a very long time. There are hardware engineers, and which I like to think of myself as a hardware engineer. There are architects of buildings, and unless you're talking about the super artsy craftsy types like just built a building at MIT, they generally make pretty good buildings. Okay, so the people who design buildings, of course, have sort of a very standard way they build things, and it's very similar to the way electrical engineers design big systems. And I have no idea what it's like to be an aeronautical engineer, but I would imagine it's something like what I'm thinking. There's a sort of very standard way to play. And that what that is that you have sort of a plan called a partie. That's what, if you're an architect of the kind that manufactures or designs structures, there's a thing called a partie, and the partie is a very general plan. Okay? A plan for something like a building which says, oh, there are some spaces. The spaces have characteristics. Some of the spaces are what's called server spaces, and some are served spaces. So, for example, a served space, this is a served space. This is a space where people actually do something. Okay? A server space is the elevator shaft, okay, or the staircase, or the hallway that goes between the various served spaces, okay, or the equipment for above the ceiling here, the false ceiling, where there's probably lots of pipes, okay, and electronic raceways, electrical raceways, and also cableways for communications, okay, as well as electrical power. Okay. So those are the server spaces for a space like this, which is a served space. There was a famous architect by the name of Louis Kahn who sort of began to talk about things like that. And when you build programs, it doesn't feel like you're doing it that way. You make some sort of grand plan, okay, which you've laid it out in some clear way, and then what you do is, as an architect, is you start filling it in. And the filling in looks like, well, I now have to worry about the distribution of electric power. Okay? So I have an overlay on my plan. The old days, they used to do this with big plastic sheets. I suspect now it's all done with CAD tools and therefore more likely to screw up. But in any case, you do it with a big plastic sheet which you draw on, okay, which shows how the electrical raceways are going to be laid out in the building. Okay? And then you have another sheet which is some of the, say, the water distribution, and another one which is the waste removal. okay, and another one which is the HVAC, right, for keeping the place cool or warm. Okay? And I suppose in the Northeast right now it matters a great deal to make it warm. Okay? Yesterday, by the way, it was 1.4 degrees Fahrenheit at my home in Arlington, Massachusetts at 8 p.m., okay, according to some computer. But in any case, and therefore likely to be wrong. Okay. Right. But that sort of idea doesn't seem to be the way we build programs. Okay? Because what's the difference? Let's see if we understand. Because actually, I think that idea works very well. Okay? The interesting thing, the difference is, if you start with the basic partie, which actually describes where walls have to go approximately and things like that. If you built a building out of that, it would work. It just wouldn't work completely. Right? It would work in the sense that you could walk in there and have a meeting. Okay? You might not have any water to drink or anything like that, but it's an actual physical building that does almost everything you need to do. Right? It has walls and a roof and all that sort of stuff. Okay? And so therefore it is operational at that level. And when you add in each layer just adds more ability, more functionality. You see, we don't build programs that have the property, as far as I can tell, that there's first a program that has spare functionality that's sort of approximately what you want. And then we elaborate it to make the more and more functionality that's needed to get the real job done. Okay? I'd love to see it that way because, in fact, it means that there's something to debug at every level that's sensible and can be so elaborated.
I think you have to be a little careful here.
Yeah?
Because I think people do actually build programs that way. But the problem is that rather than building the next layer as an add-on,
right.
It's by directly modifying the previous.
You're absolutely right. Exactly. What Chris is pointing out is I'm confusing what it means to be, yes, people are trying to do it this way, is what we're saying, but we are not providing the plastic sheets which allow the layers to be separately worked on and then laid on top of each other.
Also,
thank you. That's a very nice.
The practice of programming is reductionist, such that the removal of all redundancy is considered good practice.
Well, that's already a bad idea. I will fix that in a minute. Okay? In fact,
in this hypothetical world, there was.
And in fact, I am going to advocate something far worse than redundancy. I'm going to advocate degeneracy. Okay? Degeneracy is a much more extreme thing than redundancy, and we'll talk about it in a minute. Remind me, by the way, because I may forget. Okay? But no, degeneracy in the sense of quantum mechanics, meaning that if I have an eigenvalue with multiple eigenvectors, then that's a degenerate eigenvalue. There's many ways to satisfy that. Okay? We'll talk about it in a minute. All right. It's the same, biologists use that degeneracy in the same way, and they mean something different from redundancy. But let me get back to this. Okay, so the problem is that, yes, indeed, I don't want to modify the existing partie. That's nice. Okay? I don't want to make it complicated so I can't understand it. So let me be very clear about that. One of the kinds of programs I like building and worked on many years with Jack Wisdom are programs to do celestial mechanics calculations. Okay? Some of them we actually built hardware to support those celestial mechanics calculations because they were ridiculously hard to do with existing hardware at the time. Okay? But yeah, now, of course, your PC can beat these machines up. But don't worry about that. Suppose you have a numerical integrator. I'm going to the simplest kind of thing that might be done in celestial mechanics. You have a numerical integrator, perhaps it's a linear multi-step method. And as a consequence, what you have is something that says that the next position for the state of the system, which is maybe have many dimensions. In the case of the solar system, it usually have something like 60 dimensions or something, because you're talking about, a few dimensions for every major body. Okay? So you have the next state of the next position of the system is some linear combination of a few previous states of the previous positions. So it's usually equal to 2 times n minus 1 and minus 1 times n minus 2 for a reason, plus h squared, where h is the step size, times some linear combination of accelerations, okay, over the past n steps. Okay? That's what they look like, such a thing. Okay? If you have something which is you're dealing really serious with electrical mechanics, you might have a 12-step method, which has very high order and only works for very, very smooth orbits, which is the only kind you care about. The Earth is not going to bounce, okay, or anything like that. I hope. All right, so those are the kind of programs and what really matters in those cases is you have really round-off error is serious, and truncation error is serious, and you have to balance them so that the errors contributed by the various kinds of error are approximately equal. When that's the case, of course, then you're sort of got the right step size, okay, when those are equal. If you had your step size too long, you'd have too much truncation error, and you're wasting working so hard on the round off. Or if your step size is too short, you get too much round off, and okay, things like that. So it's an engineering problem like that. But the interesting thing is this, that the basic program is very, very simple, what I just said. 2 of those additions had better be done in higher precision than the others, the ones that are accumulating the position. Okay? And they have to be because they're not multiplied by h squared, the step size. Okay? So the numbers there are, whereas the accelerations are being multiplied by h squared, and as a consequence, the errors in them matter less because they're scaled small. Okay? So 2 of those have to be special, okay, in those additions. Often they're done by some very elaborate process, like in the case of there's something like compensated summation, which is a technique invented by Kahan, or maybe something like using one of the methods that's in Knuth. There's in volume 2, there's a theorems A through D on floating point arithmetic that explain how you can do simulated multiple precision and single precision. Or sometimes you actually have multiple precision. It depends upon the way things are working in your hardware. Okay? But you have to do this sort of thing. And as soon as you do that in the basic program, the program becomes complicated. Okay? Okay? This little nice addition that you had there now is a hairy program. And then there are other things you might say. Well, some things you have to worry about overflows and underflows, and sometimes you don't. If you have an underflow, what is floating underflow? What does that mean? Okay, floating underflow means you have your number that's not representable in the standard way. Okay, well sometimes it's an error, but sometimes it's actually something you just want to replace with a 0, or let it go, or do the right thing. Okay, and so you really want to mark a particular operation as having a particular property. This elaboration of the program is not change the basic functionality. It should be something which somehow is an overlay, okay, and not change anything. Okay? And I should be able to do it as an independent thing. I should build the basic thing, and then I should build this overlay. And I don't want my basic program to change. So that's a kind of thing that's been worrying me for a long time, because I think it would be a lot easier for us to write really good programs, okay, that lasted forever basically, and could be elaborated in ways that we hadn't thought of at the time we were writing them, if we had some way of thinking this way. Now, a lot of what we'll be talking about in this 5 days is techniques that we're sort of discovering over the 40 years approximately of Chris and I each being programmers. Okay? I'm 47 years of programming. The techniques that we've fallen into that have the property that they allow us to do additive programming. Okay? That is something, a layer can be added. The generic operations thing is clearly just something like that. Okay? Especially if the generic operations have the property that you've got a basic thing that works. My gosh, it computes linear combinations. Now all of a sudden, it can do that with matrices too, even though it was before just numbers. Right? And that's the sort of thing that's a feature that if you build it in low enough, it gives you this sort of flavor of overlay. What we showed you with this new kind of propagator programming is exactly the same thing, because if you look at what Alexei did yesterday, okay, what he was doing was showing you how you add functionality as layers. Okay, you can start out with something which is, of course, use the generic operations idea very intensively. Okay? But because of the fact that the transformation of the operation of equality in the inside of the update for a cell transformed into something which merged, so you get more that information is additive. Okay? That you're basically doing, is this a better answer rather than is this a new answer? Okay? Is this a better answer I can replace the old one with? That had the property that it allows you to iteratively add the features. Like you start out with say numbers, and all of a sudden it's no big deal to add the intervals. But the interesting thing about the intervals is, and also it's not so big deal to add going multiple directions. So you have computations that are relations as well as functions. Okay. But when you do that, it comes out so, oh my gosh, I get better inputs. I can get my inputs to refine each other. If I got a measurement that overlaps this way, another measurement that overlaps this way, and they meet somewhere and make a better result, and then that propagates back out, I get better information about my inputs. That's a thing that pops out as an emergent good property of a system that I can then add various pieces. I can add things like provenance and dependencies, okay? And now I have lots of nice properties that are things like it can answer questions: where did I get this from? Who owns it? Why do I believe this dumb thing? Oh, I've got this medical result that's obviously wrong, and there are all of the possible places where it comes from. There's one paper in common that's clearly broken, okay? And we could track it down and say Joe did the wrong experiment, okay? So that's the kind of thing that you get out of that. But then you could start adding things like search and optimal backtracking, and that sort of none of that hurts any of the previous things you've done. That's why it's important. It doesn't hurt the previous things you've done, and as a consequence, it really is additive. Okay. And now I'm going to respond to the thing you raised, okay, sir. You see, there is this idea of forgetting kind of a different kind of robustness to failure, which you have in many systems where you have redundancy. The best example in biology is your kidney is 5 times as big as it needs to be, basically. Humans have about 5 times as much kidney capacity as they need. So if you lose a significant amount of kidney, like at least one, okay, or a little more than one, you're still operational. And that's pretty amazing. That's because the kidney is made out of a zillion completely identical, for all practical purposes, tubules that stop at a little glomerulus, and there's a tubule, and it ends in a ureter. Okay, and there's a zillion of them. Okay, and then what they do is they filter blood. And the blood, all the goodies come out into the glomeruli, and then all the good stuff is reabsorbed by the tubule as it goes down. And that's what that's about. So it's a highly redundant system, but it's not a degenerate system. Biology is also full of degeneracy. Right? A nice example of degeneracy, which we don't do in our computer programs, and we ought to, and yes, it's expensive, okay, is the fact that we can do the same thing many different ways. So, for example, if it turns out that I became seriously allergic to some particular form of sugar, like galactose, okay, I don't have to eat it, right? I can get my energy, if I'm getting energy from sugar, from about 42 different sugars, and each one has a slightly different pathway for extracting the energy. Okay? But even better than that, supposing I can't eat sugar at all, that's fine. Turns out that, you can get energy out of protein, metabolizing protein. And then the pathways for that are nothing like the pathways for metabolizing sugars. On the other hand, you drink a lot of water and urinate a lot if you're getting out of protein, but that's a different problem. Okay? It's a completely different pathway, and it's, of course, much more difficult to get a lot of energy out of that. But it certainly works. And almost all biological organisms can do this sort of thing. So if you take some E. coli, okay, and they normally eat a certain kind of sugar, and you put them in a medium that's rich in actually, I think it is lactose, and not in something else which they don't normally eat. Okay, it turns out that they pop a few enzymes, and suddenly they turn on various parts of their DNA and make up enzymes that actually eat this new sugar, and they turn off the other ones. They've got all these various pathways built in. Okay? So that's the kind of thing that we don't do very much in our programming, and indeed we think of that as expensive. And you can see it all the time. When you build some big system, there are lots and lots of plan fragments that we certainly discard. I got code that does something one way. I got code that does something the other way. Same thing. I've got code that does it a third way, and I pick one of them and use it. I don't have all three of them there. Okay? Now, partly that's dangerous because I don't have the diversity that protects things. It could be that their really overlap of the capabilities is not exact. And so this particular piece of code solves this problem, and this piece of code solves a different problem. And if you look at the Venn diagram, a few of them cover a lot larger area. And if it was played right, I could get a bigger and more general program. Also, there's a redundancy power there in that if I'm in the set, which is the intersection, and once there's a failure, then I can get an error comment sent to me, the author, and yet the system keeps running, because it could be doing something like checking and voting, okay, and things like that. But when you have things like propagation of constraints, you have constraint boxes which are more powerful than just function boxes. You get even a more powerful kind of value out of degeneracy, which is the overlapping of many ways of solving a problem rather than many copies of the same way of solving a problem. Okay? Here's an example that we do all the time in science. Okay, science is built this way. Consider my favorite subject, which is classical mechanics or physics, or that sort of theoretical physics. Okay. Suppose you want to solve problems that have to do with moving objects. Normally, it's called mechanics, right? How that thing does its thing, and that's what mechanics is: description of the motion, what motions are possible and what motions are not possible, and things like that. Okay. Well, there actually are three completely overlapping formulations of classical mechanics that appear to be equal in some sense, but they're all necessary. There's the Lagrangian formulation, there's the Hamiltonian formulation, and there's the Newtonian vectoral formulation. Okay? In the case where they are, all of them are applicable, they get the same answer. Okay? And you could show that you could prove that they're going to be the same, because in those cases, then Newton's equations are the Lagrange equations, and by a small transformation, they're the Hamilton's equations. Okay? However, these give you different information. First of all, they're not completely overlapping. You can't do variational mechanics, which is Hamiltonian and Lagrangian, on things with friction. It doesn't work. Okay? Friction is a strange kind of world, because what it is, it means I'm ignoring something. Friction is I'm ignoring the degrees of freedom that are in the thing that's getting hot when the two things rub. Okay? And as a consequence, that piece of the universe is being abstracted away. Okay? In order to solve problems with things like friction, I indeed have to use Newton's vectoral methods, which are a pain in the ass, because I have to do a lot of geometry. Right? That's the cost. The benefit is I have to add vectors and things like that. The benefit is that I can solve problems with friction. On the other hand, if I don't have friction, if I've got something which is dissipationless, like, for example, the motion of the planets or the motions of fundamental particles, okay, or even things like abstractions like a driven pendulum like this, okay, then the other variational methods actually make sense. Okay? And the variational methods, which have other advantages. In the Lagrangian formulation, I see things that I can't see any other way. I see the connection of the symmetries of the universe to the conservation laws. For every continuous symmetry, there is a conservation law. The fact that I can do an experiment now and I can do it 5 minutes from now and I get the same result, shifted in time, is the same thing as conservation of energy. The fact that I can do it here or here is conservation of momentum, and the fact that I can do it this way is conservation of angular momentum. That is the same thing. That's Noether's theorem. Okay? And that only appears if you think the Lagrangian formulation. Right? If you look at the Hamiltonian formulation, you see other power that doesn't exist and you can't get out of it. You see that you discover things like the conservation of the volume in phase space, which is equivalent to the conservation of information. It says that everything's reversible, that the past is as much determining the present and the present determining the past and the future. I mean, all that's the same. Okay. The other thing you see is you learn all about things like that. Because of that, there's area preservation in phase evolution, which forces you to get things like chaos. Chaos is a consequence of that. It's a consequence of area preservation, actually. Okay? And so these are things that you discover and understand that you can't see from the other formulations. Okay? So they're valuable. And you know what? When you go to things like quantum mechanics and relativity, Newton's formulation starts dying, and these others take over and remain relevant. Okay? So in fact, there's what you've got is degeneracy in the structure of the subject. And you know what? The degeneracy actually is an overlap where there are constraints among them. So, for example, the Legendre transformation that connects a Lagrangian formulation and a Hamiltonian formulation is a little thing that says the product of two things is the sum of two other things, which is always true. Okay, and it's computed. You can compute it and you keep them all the same around the same time. So that's the kind of thing that we lose by not having our programming degenerate. Okay? So it's essential. I believe that what we're really on the boundary of, because suddenly there's a transformation. Suddenly there's enough resources. To be very clear, computation is pretty close to free. Now, communication may be expensive, but computation is pretty close to free. Yes, I know somebody's complaining about how many kilowatts it takes to do a search, kilowatt hours, excuse me.
Part of the thing you're talking about is extra code.
Yes.
As opposed to extra computation. And extra code is pretty much free.
That's right. Okay. And I think in general, even extra computation is pretty much free at this point, because the only resource that ultimately is going to cost is energy, and that energy, well, is 1,370 watts per square meter falling on the Earth from the sun, and it's very hard to use that up. Okay. Huh?
Because extra code requires
Yes, but we make that code anyway. That's what I'm
It's free to
saying.
have it around.
I'm saying we have that code anyway. We don't incorporate them into one thing. Okay? We don't make the code bundles that we have are not the kind of thing that you have when you build even when you build an electrical system. There's lots of degenerate stuff in a communications receiver. If you take something like or an oscilloscope, you take some of the really hairy kinds of electronics, not the consumer electronics. Communications receiver is probably the most complicated thing that a person every day might encounter. It's an extraordinarily hairy piece of machinery, okay? And by golly, it is heavily degenerate. It's got all the manners of ways of squeezing those those words out of that noise. You're basically got synchronous detectors. The synchronous detector may be turned on or off. And, why would you do that? Because you could also do a peak detector, and it's there too. And there's about 42 different things in there for the purpose of squeezing out notch filters and bandpass filters and smooth filters that can move around the IF amplifier and things like that. All very complicated. Okay?
As opposed to cell
A cell phone is one where you have no control.
phones. Cell phone is not,
That's a piece
cell phone
of,
has a really trivial function.
but also a cell phone's a piece of junk.
Yeah.
It doesn't cost very much. A communications receiver costs, $10,000 for a good one, right? So that's the point. Okay, the difficulty here is that if we really wanted to make a class act like you do with things like a communications receiver or a high quality oscilloscope or stuff like that, there are things we know that we're not doing now. And and there are ways of behaving as programmers that we're not behaving now. And I think what Chris and I and Alexi and a few other people are trying to do is to try to make infrastructure for supporting real class act programming. Okay? I think that's all I really wanted to say. Okay? Yes, sir.
So you make this, you show me a concrete example, and here's the overlay I want you to put on your program.
Yes, actually.
So you choose the program, and I want the testing overlay.
Okay, Alexi, why don't you tell them about the testing overlay we have on this one?
What?
Yes, actually you have. No, for example, you wrote it. Okay, it's a very interesting one, actually, because, well, the tech thing, too. It's remember Knuth's idea of literate programming, okay? There's already one good thing, okay? What he's got is he's got code interwoven with the comments so as to make a publication, okay? Such that you can execute this giant block as either text is either a program to be run on a computer or a program to be run on a human. That's what text is. Okay? And in fact, that's a very complicated job. I think that Knuth's job isn't very attractive the way he did it. Okay? I think in general it's overly detailed without being easy to work with. But Alexi has recently done a similar thing with the kind of the paper, it turns out, that describes the system that he talked about yesterday, and Chris talked a little bit about today. Okay, happens to be executable in both ways, and there's a testing overlay built into it, such that you can say, run tests, and it does it. Okay. But the fundamental piece of machinery underneath is a very clear, separable piece of machinery. Okay? And you can, in fact, execute it in ways to also extract the various pieces. Okay? Now, that was an accident. That it turned out that what he just did is something that answers your question, but it's an example. Okay? I don't think he was aiming at doing that to answer your question.
Well, so look at Google says this job on testing tree, which is required to be separate from the main code. I think that is actually an example of an overlay of that kind. It doesn't actually, what it does is it exercises the code, but it isn't a part of it. And the code is fine without that being around.
Mm-hmm.
But I'm not sure if you were thinking of something else.
That's a fine example. I don't actually like that model because now the more places that I have.
Maybe the right thing is to give people
Actually, it occurs to me that the advantage of that model is you can take the partee and look at it without the test transparency. And you can take the test transparency and look at it without the partee. But you can't put them on top of each other.
Yes.
I think that's the place where you lose.
Right, so I can't easily check that every function has a test.
Right.
And we're actually, I want to almost force somebody to write a test for every function that they write. So it's just all syntactically sort of in the same place, but only look at that test when I actually care about that test and not look at it when I don't care.
And I would say that why don't you take that off, Jerry? This is silly. And I would say that that is because we don't have language tools that support that kind of thing. And we could, but we just don't.
Yes. And in particular, I think it's crucial to make language tools that, wait a second, that actually support both degenerate programming and layered programming. Okay, and that's what I think is the goal of what we've been working on for the last few years, actually. Go ahead.
So on the testing front, I was trying to figure out how to test JavaScript code which makes extensive use of closures for information hiding. And so since it's most of the purpose of this code are security related, you want to test it rather thoroughly. But using closures for security hiding means there's almost always no public name that you can access a test by, because the closures are, and so yeah, and so the way we came up to test that was by embedding tests that look like running something in an interactive shell in comments. And so you have a specially formatted comment which says updoc test, add updoc, and then you have a series of lines which are some expression that can be evaluated in the context the comment appears, and then some representation of what you would expect the result of that to be.
So you have some sort of a compiler that runs
Yeah.
in a different way.
And existing IDEs are able to collapse blocks right now, so you can think of that as a way to, if an IDE were to collapse blocks of a particular type, that might be equivalent to removing or showing a particular layer. But I also had a question, which was,
Yes,
what do you think of aspect-oriented programming?
Aspect-oriented, okay. What do I think of aspect-oriented programming? I don't think very much about it because I don't know a lot about it, although I know Gregor very well, who is sort of inventing that. I actually think it's a step in the right direction. Okay, it had a good idea to begin with, okay, but it got very tied up in the particular details of the Java. What's it called? What's the name for it? Aspect J. Okay, and in order to become relevant fast, I think it sort of strangled itself in Aspect J. Okay, so, but I think that the original impetus for it, which came from Gregor, was absolutely right. Okay, he's a person with the right emotional state about programming. How's that?
So, independent of Aspect J, one of the other problems that aspect-oriented program in general empirically has run into is that the separation of layers ends up being tightly interwound after a little while. And so, I mean, part of the problem is that although at outset it may be very clear what the building is and what each of the layers on top of it is, as time goes on, one realizes that the separation into layers that one had originally come up with were poor. And as you continue to make a change, you come to realize that, your sewage system actually makes a difference to the way in which you should lay out your electrical wiring. And I think that that's one of the fundamental differences between the way in which computer programs are written compared to the way in which a house is built. Generally, once a house is built, it stays pretty much a house, whereas a computer program that started out as a house ends up being a car or a horse.
Right. Yes, indeed. No, I think that makes perfect sense. I think you're absolutely right. But I think the difficulty, but we do ourselves a great disservice by not trying to make it like a house. Okay, I think that the part of the reason why the Aspect J thing is having the problems you're saying is because it's inducing us to in fact build the wrong layers sometimes. Okay.
So,
Yeah.
I also think it's maybe there's not enough experience
Sure.
with how to build layers yet.
That's right. Yes, sir.
So maybe I'm disagreeing with you and maybe not, but it seems to me that the really powerful innovations in the last decade in programming have not been technical but sociological ones. Because programming is basically a distributed reasoning process, and all of the problems that I see are essentially failures of distributed reasoning. The ability to have one programmer's reasoning mesh with another programmer's reason and not share entirely the contents of their brains. And I'll give you an example that we talked about unit tests. you know, when programmers are deciding what changes to make, they make a risk evaluation. And there's a rule of thumb that says that, you know, changes that affect a large number of lines of code are inherently more risky than changes that, as a rule of thumb, than small numbers. But there's some kinds of changes that you can make that affect the entire program and yet are very safe, like renaming a variable, because the compiler will tell you every place you made a mistake. Unit tests do that on the semantic level, what the compiler would do on the syntactic level. Essentially, they force you to write down all your axioms, okay? And a given function may have hundreds of axioms, you know, which is something I've discovered in the process. So essentially, it's a communication tool between these different reasoning processes. And because the risk is reduced, it allows you to take larger jumps, you know, the homeostasis of risk and all that. So.
Okay, but what was the actual disagreement?
Okay, I'm saying that the disagreement is you're talking about better tools and better languages, and I'm just wondering if better practices is not where we're going.
I don't see that that's a disagreement. I think we're in violent agreement. Okay, I think that you know, it's not that there's one thing or another. I think we really want both. Okay, we want better tools for thinking more clearly, for helping us think clearly, which is what programming is, and we want ways of making it easier for people to collaborate, which is what you're talking about.
Well,
Yeah.
here, so what you just said is evidence in favor of that. So you basically were talking about testing. Okay, testing is a technological or linguistic change that allows you to write down your assumptions, right? But then sociologically, you have this other thing where you basically require people to do it in order to make sure that there's communication. So it's sort of both a sociological thing and a technical thing, right? There was no testing when I learned how to program. That's a big deal.
Right.
It's a very important.
Yeah. Anyway, I think we've just run out of time. This is the end of it, and I hope you enjoyed it, and I hope it was helpful to some of you. And I think that now I go back to MIT, and I allow Chris to go back to work.